so this is lesson 3.4, Symmetries of Graphs, but we're going to start with the drill that's reviewing the translations of functions. All right, so let's start with number 1. All right, whenever I'm asked to graph a function and write the translation rule, I typically write the translation rule first. The very first thing that I do is I go through and I figure out what the parent function is. So for number 1, I recognize that it's y equals x squared. This one I know is y equals the absolute value of x. And number 3 is y equals 1 divided by x. It gives me an idea of what the graphs are going to look like. This is going to be a quadratic. This is going to be a V-shaped graph. And this is going to be my graph with my two curves in the first and third quadrants. Okay? All right, now I'm going to write the translation rule for each. So when I go to write the translation rule, put my capital T, and I look at my x. Now in the equation x lies, so this is actually going to be x plus 2. Y tells the truth, so that is y plus 1. You could also write it in subscript notation. So I'm going to move 2 to the right and 1 up, and then I'm going to draw my quadratic. Okay, for number 2, let's see, my translation rule. It says x plus 4, which means it's actually going to be x minus 4 in the rule. And nothing happened to y. I can also write it in subscript notation. And that means I'm going to go to the left 4, 1, 2, 3, 4, and I will not move up at all, and I'll draw my V. And for number 3, I'm going to write my translation rule. Look at the equation that says x plus 3, so the rule must be x minus 3. And y tells the truth, so y minus 2. I could also write it in subscript notation. So I'm going to translate 3 to the left, 1, 2, 3, and down 2. That is going to provide me my new center where my asymptotes are going to go through. So I'm actually going to sketch my asymptotes there. That's the new place where my asymptotes are, and then I draw my curve so that it looks like my parent function. Right. Now down here in numbers 4 through 6, I'm asked to write the rule and the equation for each graph. So again, the first thing I always do is figure out the parent. So when I look at this, I can tell it's a quadratic. I know that it's going to be a y equals x squared. This is a V-shaped graph, so it's going to be y equals the absolute value of x. And this is going to be y equals 1 divided by x squared. So once I figure out what my parent function is, then I'm going to write my rule, which will allow me to write my equation. So my rule, my translation rule, is, let's see, normally I would be here. I'm going 1, 2, 3 to the left, x minus 3, and 1 down, y minus 1. I could have also written it as negative 3, negative 1. Well, now that I have my rule, I can say y equals x plus 3 squared. Notice that the rule and the equation should be opposite when it comes to x, because x lies. But then the y should tell the truth. So there's my equation. All right, for number 5, I notice that my translation rule, x is moved 1, 2, 3, 4 to the right, so x plus 4. And I didn't move it all on the y. I could also think of that as 4, 0. When I go to write my equation, y equals the absolute value. Since the rule says plus 4, the equation has to say minus 4. And then nothing on the end. If you want to put plus 0 as a placeholder, you can. And my last one here, number 6. My translation rule, let's see what I'm going to get here. Normally, 0, 0 would be where my asymptotes go through. I notice that my asymptotes are here. So they're 1, 2, 3 to the left, so x minus 3. Doesn't look like my asymptote has moved up at all, so that's just y. You can also write it in subscript notation, -3, 0. Then I go to write my equation, y equals 1 divided by, in parentheses, I'm going to put x plus 3, and then nothing for the y. Okay, so we're going to be talking about symmetries of graphs, and we're going to identify graphs as either even or odd, and we're going to use translations to find some of those symmetries. So we have two basic symmetries that we look at. We look at reflection symmetric over the y-axis. We do not have a symmetry that we look at that's reflection symmetric over the x-axis. We just look at it over the y-axis. And my other type of symmetry is rotation symmetric 180 degrees around the origin. So I want you to think about this, the parent functions that we have. And I want you to think about which of my parent functions are reflection symmetric over the y-axis. One of them, sketch a graph of it, you'll be able to then obviously see, is a quadratic. Y equals x squared. That is reflection symmetric over the y-axis. It means that if I was to reflect it over the y-axis, you wouldn't even realize that I had reflected it. If you folded this part over to here and this part over to here, you wouldn't even know that I had switched them. Another one is the absolute value parent function. Y equals the absolute value of x. Think about it. If I reflect it over the y-axis, this piece moves to here, this piece to here. We can't even tell that I moved anything. And my third one is my y equals 1, my inverse square. Y equals 1 divided by x squared. If I was to reflect that over the y-axis, you wouldn't even realize that I had reflected anything. So the general rule of thumb is that when you have an ordered pair, x, y, and you reflect it over the y, you end up with the opposite of x. So if this was the ordered pair, let's say 3, 2, if I reflect it over here, it's going to be the ordered pair -3, 2. So it becomes negative x, but notice that the y coordinate didn't change. 3, 2, when it reflects, is -3, 2. Okay? And whenever we have a function that is reflection symmetric over the y-axis, when we get the x becomes negative x and the y stays the same, we say that this is an even function. Now, I do notice that we have even exponents. However, that's not part of the definition of even, and we're going to look at that in just a little bit. But we say that something is even whenever it is reflection symmetric over the y-axis. So it has to be reflection symmetric over y-axis. Therefore, xy becomes negative xy. Right, so now we're going to look at the other types of parent functions that are rotation symmetric 180 degrees around the origin. I've got my cubic graph. if I was to rotate this 180 degrees either direction around the origin, this piece would come down and fit here, this piece would move up there, and it would look like I never moved the graph. Another one, the very first function that you ever learned about, the linear function. Same thing, you rotate this piece to here, this piece up to here, and you're going to have the exact same graph. You wouldn't even know that you had moved it. And then we have our inverse graph, y equals 1 divided by x. Again, these pieces, if you were to rotate them around the origin, this piece would move to here, this part of the graph up to here, and you would never know that I had made any changes. Now, in this instance, when we rotate our ordered pair x, y, okay, if we're to rotate from here down to here, or here over to here, both the x and the y change. So we're rotating 180 degrees around the origin. When we do that, we get opposite of x, opposite of y. They're both going to change. This type of function is known as odd. That means that it is rotation symmetric, 180 degrees around the origin. Therefore, xy rotates and becomes opposite of x, opposite of y. Right, I do want you to notice that we only have 6 of our parent functions here. Every graph doesn't have symmetry. For instance, y equals the square root of x, where the graph looks like this. This is not reflection symmetric, nor is it rotation symmetric. So we are going to say that this is neither. Same thing with my exponential graph, y equals 2 to the x. When I have that exponential curve, it is also going to be neither. So every graph is not even or odd. There are some graphs that are classified as neither. All right, so we're going to sketch the graph of f of x equals 1 divided by x. In order to do this semi-accurately, I just have to realize that my asymptotes, and I'm actually going to draw those in with a highlighter so that you can see that this is an asymptote, and this is an asymptote for this equation here. Then my sketch would look like that. Okay. Now, give equations for the asymptotes of this graph. Well, this horizontal line here, on every single ordered pair of this horizontal line on the x-axis, y equals 0. So right here we have the point 1, 0. Here we have the point 4, 0. Here we have the point -3, 0. In every one of them, the y coordinate is 0, so we call this line y equals 0. Then we have this vertical asymptote, and the thing that every ordered pair on the vertical asymptote has in common is that its x-coordinate is 0. This is 0, 1. This is 0, -3, 0, -5, 0, 10, and 0, 10. So x equals 0 is the other asymptote for this parent function. Now our next question says, find the rule of translation for this equation and then graph it. So let's just work on finding the translation rule. Well, I see in my equation it's x plus 3, which means it's going to be x minus 3 in the rule. And I see that it's a -2 and y tells the truth. Or I could write it as t -3, -2.